a few minutes before we really start. I just want to mention this webinar will be recorded and it will be available afterwards in the internet. You will have access to it over the link where you log into this webinar as well. Okay, I think now we have 2 minutes or 3 minutes past 3. Let's start with our MKS webinar. First of all, I want to welcome everyone to this MKS webinar or EU talk. Today, we have a talk about the principle of vacuum measurement. The presenter will be Marco Schott. He is for more than 20 years, he is now within MKS Instruments, and he has a lot of different functions during the time, and he is a senior application engineer with a lot of experience in all kinds of vacuum. So, Marcus, please start the talk.
Thank you very much, Bruno, for this short introduction. It's a very exclusive audience today. I see 5 people in the audience, so thanks a lot for joining. The title of my talk today will be Principles of Vacuum Measurement. I will start with a short overview of the contents that I'm going to give to you. So first of all, after a brief introduction of our company, I will talk about various pressure regimes. I give a brief glimpse into history, followed by the principle of direct pressure measurement, followed by 4 principles of indirect pressure measurements. I will then move over to the product side, so to the technological realization of various principles for pressure measurements, starting with capacitance manometers, moving on to thermal conductivity gauges, and I will finish off the presentation with a brief glimpse to a possibility to partially measure pressures or various gases, and concluded will the presentation be by a short glimpse into the future. MKS as a company has always been a driver for enablement of technologies across markets. We've been there for more than 50 years. Actually, we are turning 60 this year. And we started off actually with pressure measurement, especially the measurement of vacuum in the vacuum regime below atmosphere. And we have grown over the years, not only by organically growing, but also through acquisitions of various companies. So basically, our fields of actions are semiconductors and everything else which we combine as advanced markets. Since we will be speaking about vacuum, and vacuum usually occurs in a vacuum chamber, let me give you a brief, well, let's say movie thingy about the evolvement of products around the vacuum chamber since our initial public offering in the year 1999. As I said, we have made various acquisitions over the year. The last one has finished just a few weeks ago by the addition of a company called Photon Control. And you have seen the number of instruments around the vacuum chamber growing. In all those fields, MKS is present in all those fields MKS has products. MKS is made of 3 basic pillars. We call vacuum and analysis. This is the part of MKS which I belong to. There are 2 other parts of MKS, light and motion, which deals with precision positioning as well as with lasers. There is another branch of MKS called equipments and solutions, and they have their special tools, for example, of drilling holes into PCBs as well as creating wires for PCBs. But since we are working for vacuum and analysis, the briefest of overview in which fields vacuum and analysis is present. First of all, the topic of our presentation here is pressure and vacuum measurement. And of course, we have a lot of products for that. Very closely connected to pressure measurement is gas delivery and gas delivery control. In many vacuum processes, you need power and also reactive gas. And of course, if you create vacuum and put gases into it and put energy into that and create processes that change the materials due to chemical reactions or forced reactions due to the influence of plasma, you also want to know what's inside your vacuum chamber. And for that, we have a large analytical and controls division. And finally, we are at a point where I can start with the actual presentation. Let's start with pressure regimes. Traditionally, the lower pressure end is divided into various sections with certain names to it. So just below atmosphere, down to the pressure of about 1 millibar, which is a thousandth of the atmospheric pressure, there's a regime we call rough vacuum, followed by a regime we call fine vacuum, between 10 to the minus 3 millibar and 1 millibar, so a millionth to a thousandth of the atmospheric pressure. It goes on to the high vacuum regime, which is the pressure regime between 10 to the minus 7 millibar and 10 to the minus 3 millibar, followed by the ultra high vacuum pressure regime, which is 10 to the minus 12, 10 to the minus 11, all the way up to 10 to the minus 7 millibar. Below that, there are other names for other vacuum regimes, but the lower the pressure gets, the less technologically important those pressure regimes will be. Which means that we will focus on the 4 pressure regimes depicted here: rough vacuum, fine vacuum, high vacuum, and ultra high vacuum. The various pressure regimes can be described using various parameters. For example, the rough vacuum and also the fine vacuum can be described as a regime where thermal conductivity is important. Below the pressure of 10 to the minus 3 or 10 to the minus 4 millibar, thermal conductivity of a given gas is near 0, which makes a vacuum a very effective thermal isolator. But if you want to take a look at the pressures between 10 to the minus 11, for example, and 10 to the minus 3 millibar, then the behavior of single molecules or atoms become important. This is in connection with the free path that any particle, be it molecule or atom, can travel before it meets or even hits another particle. And that's the middle column of my slide here, where the mean free paths of molecules are depicted until a collision occurs. To give you a drastic example is the pressure in the intergalactic regime between galaxies in the universe. You can have as little as 1 particle per square kilometer, which would translate into a pressure of, I just calculated it, 10 to the minus 37 millibar, which is very low. The briefest of history. The first true pressure measurement was already done in the 17th century by a gentleman named Evangelista Torricelli. He created the mercury barometer. And the mercury barometer was actually making use of the physical definition of the pressure, in which the pressure is the force per area. Torricelli created the first mercury barometer, where a pool of mercury was in contact with the atmospheric pressure. And Torricelli used a glass tube, which he evacuated by one of the first vacuum pumps available during that time. And he just stuck the glass tube with one end open into the pool of mercury. And he observed that inside the evacuated glass tube, a mercury column was rising to a certain height. It rose about 760 millimeters, so he really used a very long vacuum tube. That was also a technological challenge during his time. But in the end, he created the first barometer, measuring the atmospheric pressure by measuring the height of a mercury column. So the atmospheric pressure really is equal to 760 millimeters height of a mercury column. And believe it or not, but the mercury column based barometer is still the prime reference for measuring pressures around atmosphere down to about 1 millibar. It's still being used as mercury barometers are still being used after all this time, after almost 400 years. After 400 years, Torricelli, because of his deeds, so to speak, became the namesake of the first pressure unit. So the first pressure unit is named after Torricelli, and that's the pressure unit torr. Torr is equal to 1 millimeter of the height of the mercury column, and 760 millimeters of mercury column actually present the atmospheric pressure. This kind of pressure measurement again makes use of the physical definition of the pressure, where the pressure is force per atmosphere. Over the years, torr became outdated as the pressure measurement unit. Other pressure measurement units, for example, Pascal or millibar, are being used nowadays. That vacuum can be a very forceful thing was shown with the famous Magdeburg half spheres around the time where Torricelli has lived. With the Magdeburg half spheres, it was shown that the atmospheric pressure really has a lot of force, a lot of power. The Magdeburg half spheres are basically two parts of a vacuum vessel that, when evacuated, cannot be torn apart by a host of about 12 forces. That's because the force needed to take those half spheres apart is equal to the difference between the atmospheric pressure and the pressure within the half spheres. So that concludes my brief glimpse of the history. Let's now get to the technology of actually making pressure measurement devices. And I divided that part into basically two parts. I have a part about direct pressure measurement, followed by a part about indirect pressure measurement. Direct pressure measurement makes use of the physical definition of the pressure. Again, P equals F over A, force on a given area. And when you apply force to a material, mechanical deformation occurs. if you press on the table in front of you, and if you press really hard, you will slightly deflect the table in front of you. And that slight deflection is an example of mechanical deformation. So you can use that deformation, that mechanical deformation, to directly drive hands on a kind of watch-like manometer. And an example for that would be a burden gauge. A burden gauge is basically a tube into which a curved tube into which pressure is introduced, and depending on the amount of pressure, that curved tube will deflect, and that deflection can be used on a scale and gives you the pressure value inside the tube. You can use much smaller deflections, mechanical deflections. For example, in a capacitance manometer, where you deflect a very thin metallic foil by the pressure that's being applied to it. That deflection of the thin metallic foil actually creates a change of distance to another element within a manometer, and that change of distance can be detected electrically by an electrical capacitance that is being changed due to the fact that the distance between two electrodes is being changed due to the fact that the diaphragm is being deformed, is being deflected. There's another way of using mechanical deflection, and that's the resistive technology. So in a strain-based gauge, for example, a resistor, which is in close contact to the material that's being deformed, creates a change in resistance when the resistor and when the material that's being deformed and the resistor with it is changed. So the change of resistance can also be detected and processed as a pressure value. So again, the direct pressure measurement principle makes use of the physical definition of the pressure, which is force per area. And make a mental note that there is no material property of the gases that create the force on the given area is present. So the direct pressure measurement is independent of the gas that it measures. As opposed to the direct pressure measurement, there is, of course, indirect pressure measurement. Depending on the pressure regime that you want to measure with indirect pressure measurements, you can use various properties of the gases that you want to measure the pressure of. The pressure measurement of gases can be based on the collective behavior of the gas molecules and gas atoms, or it can be based on the behavior of a single molecule or a single atom. So what you basically do is you count particles in a given volume. For example, using the gas density measurement, which the physical realization of which is a thermal conductivity gauge, or in other words, a heat loss gauge. For any of those who have heard the term, the Pirani gauge really is what I am talking about here. You do have a heated wire that is being exposed to the pressure which it needs to measure. And because of the gas density, the heated wire will lose energy. That energy loss or heat loss can be detected in a very simple circuit. You see a representation on the slide here. The so-called Wheatstone bridge can be used to detect even subtle changes of the sensing elements resistivity, creating a pressure measurement that's good for about 10 to the minus 3 all the way up to atmosphere. And that's an example of a gas density-based measurement. If you want to dive into it, you can actually take the ideal gas law, P times V equals N times K times T. And what you do really is you count particles or particle density for that matter. If you go below 10 to the minus 3 millibar or 10 to the minus 4 millibar, and my slide speaks of torr, I apologize for that. So I should have taken torr or millibar, but between 10 to the minus 4 and 10 millibar, and even all the way up to atmosphere, you can use thermal conductivity gauges to measure the pressure. Below 10 to the minus 4 millibars, the molecules and atoms actually act independently of each other, which means that you will not have a lot of heat loss anymore, so you cannot use that principle. You need to use another principle. For example, you can use an ionization gauge that makes use of ionization occurring from actively created electrons that are being accelerated in an electrical field. And when electrical ions that are being, or electrons that are being accelerated in an electrical field hit other particles present, be it molecules or atoms, the energy of the accelerated electrons can be high enough to ionize those particles already present in the volume in which you want to measure the pressure within your pressure gauge, so to speak. So whenever a particle is being ionized, be it an atom or be it a molecule, it will of course see the electrical field that has accelerated the electrons, causing the ionization. So the ion and the lost electron will be torn apart from each other and eventually hit the electrodes. But when they hit, when the ions and the electrons, of course, hit the electrodes, they will electrically recombine, which provides a short pulse of current. Integrating all those current pulses will give you an electrical current. Mind you, it is very, very small, picoamperes, but that value of ion current is a representation of the pressure or of the number of atoms or molecules within your pressure gauge, and thus, due to the ideal gas law again, it is a representation of the pressure within your vacuum gauge. So ionization gauges make use of ionizing particles within your vacuum gauge, and then counting the current spikes that will occur during the recombination of those ionized particles. You can do that by either actively sending out electrons using a hot wire, hence the name hot cathode, or you can use large electrical fields and make use of free charged particles that are already there. You might ask, why should I use actively created electrons when there are already charged particles in your volume? Well, that's because the number of charged particles inside a given volume is always very, very small. You might also ask, why are they there at all? Well, there's cosmic radiation, really cosmic radiation from outer space and so on. So whenever a cosmic particle, a particle with very high energy, hits by coincidence any atom or molecule inside your vacuum gauge, it can ionize that. Now you need larger electrical fields because you want to make use of basically electron multiplying. So when you use large electrical fields and you rely on already present charged particles, you can create an avalanche of ionization, and that avalanche will then produce enough current that can also be detected as a representation of the pressure measured. So there are two ways of using ionization gauges, either with actively created particles to do the ionization, or relying on free charged particles that are already there and that are being created by cosmic radiation. Then you need to also take care about the efficiency with which the ionization within a cold cathode can occur. So the technical realization of that is you increase the path of the charged particles within your ionization gauge using magnets. The magnets, the magnetic field, will force the charged particles on basically spirals on paths that have the form of spirals. So the residence time of any charged particle within such a configuration is much higher than without the magnets, and that also increases the efficiency of the pressure measurement, and it gives you the opportunity to measure pressures down to 10 to the minus 11 millibars, or even lower than that, with both cold cathodes and hot cathodes. There are limitations, of course, because a pressure gauge can only have a certain volume, and that's the particles within that limited volume is all the particles you can use, or are all the particles you can work with to create, well, the current or the current spikes or current pulses that you need to count the particles and, in fact, to measure the pressures. There's another very special way of measuring the pressure, and that's also a very cool application, really, of the properties of gases and surfaces. And that principle is based on the molecular drag, basically the inertia of a particle of a certain size. Particles, atoms, or molecules have a certain mass, and the mass has an inertia, and that inertia can be used to actually decelerate a sensing element. The sensing element into in a device that's based on molecular drag is a levitating stainless steel ball. So you use magnets and levitate a ball, and then you use magnetic fields to actually make the ball spin. So it sits there in the vacuum, freely spinning around, being happy, and then molecules or atoms hit it and actually stick to the surface for a very short time. That's a property of surfaces and particles. They adsorb, but they also desorb after a certain time. But when they actually adsorb, when they stick to the surface, the whole rotating element becomes a little bit heavier. And when it leaves the surface, the rotating ball has a slightly smaller frequency, turning frequency, than before. So you can use the deceleration rate to count the particles that have actually stuck to the surface over a certain time. And when you count particles, you have, again, a representation of the pressure within your sensing element. So a spinning rotor gauge is another way of indirectly measuring the pressure. How do you make all that into a product? Well, you can classify gauge types. Okay, so here's a little overview of the major vacuum gauge types. You can use simple mechanical gauges. Think of the burden manometer the one where a curved tube is being deflected. I'm not sure if one can see that. Pressure from that side will deflect the tube, and that can turn a hand. So that's an example of a mechanical gauge. Thermal gauges, we talked about thermal conductivity, that's Pirani gauges and the like, is another example of the technological realization of a pressure measurement device. There are strain gauges, where you use the electrical resistance that's changed due to the deformation of the resistor. You can use capacitance gauges. Capacitance gauges make use of the electrical capacity that's being changed due to the deflection and the distance change to another element. You can have ionization gauges for very low pressures, and you can have the spinning rotor gauge, which gives you an excellent accuracy down to 10 to the minus 7 millibar. Being MKS, of course, we have a lot of capacitance manometers. The capacitance manometer is actually the product with which MKS was founded in 1961. And we very quickly discovered that it is ideally suited to very, very precisely measure the pressure over a multitude of magnitudes. Any capacitance manometer that's on the market, especially the MKS Baratrons, have a dynamic range of 4 decades, 4 orders of magnitude. It can measure the pressure down to 10 to the minus 6 millibar in a very extreme case, but there are also capacitance manometers that measure pressures all the way up to 200 bars, depending on the application. Most of the applications that MKS touches are involved in the vacuum regime, especially in the vacuum regime between, say, 10 millibar and 10 to the minus 4 millibar. That's ideally suited. That's an ideally suited pressure regime for a baratron or a capacitance manometer. It is basically made up of 2 parts. I hope one can see. I hope one can see my cursor. The deflected diaphragm, the element that's being deflected due to the force that's being applied to it, is that little curved line here. Okay. To the left of it, you have your vacuum process, where you want to measure the pressure. All this here is made of metal. The diaphragm is made of metal. It is welded to the metal compartment of the sensor. So only this part here, the dark blue part, is being exposed to the pressure. Behind that, there's another volume that does not see the process at all. That volume is being kept at a very, very low pressure, 10 to the minus 7 millibar or lower, and it contains more electrical components or more components being used to actually enable the electrical detection of the capacitance change. So what you basically see here is an electrical configuration called a capacitor. In fact, what you see here, or what you could see here, if you look very, very closely, is a configuration with 2 capacitors. And those 2 capacitances are being connected to an electronics, and it will then measure absolute pressure in the dark blue area. The advantage of capacitance manometers are, first of all, they are direct pressure measurement devices, so they measure the pressure independent of the gas type. They offer excellent accuracy. We have extreme baratron, I call them extreme baratrons, baratrons being used in calibration labs that offer an accuracy of 0.05% of the measured value. And even the most common process manometers for technological applications such as semiconductor or thin film deposition still usually offer accuracies of about 0.1% of reading, plus a couple of other components of the measurement uncertainty. And they all have at least 3 decades, in most cases even 4 orders of magnitude of measurement range. And the extreme baratron I mentioned earlier actually have has a measurement range of 5 decades, 5 orders of magnitude. Okay, so that's one workhorse, and a very, very precise workhorse as well. Another workhorse where precision is not that much of a topic are thermal conductivity gauges, and the prime example for that, of course, is a Pirani gauge. There are many ways of building Pirani gauges. Thermal conductivity gauges is a synonym for a Pirani gauge. There are the traditional ways. There are traditional ways of building Piranis, and there are more advanced ways of building Piranis. We do have both the traditional Piranis, and we have a product line called Micro Piranis, which makes use of a MEMS-based thermal conductivity sensor, heat loss sensor. You see some examples on the left-hand side for traditional Piranis, and on the right-hand side for Micro Piranis. To give you an Vorstellung, to give you a feeling of the size, this diameter here is 30 millimeter. So the whole construction of a Pirani, of a Micro Pirani transducer, is not more than 5 centimeters in that dimension. So very, very compact, yet very wide range gauge. I will not be silent about the disadvantage. The disadvantage, of course, is that it is a gas-dependent measurement, and it's also not as accurate as a measurement with capacitance manometer. The gas dependency of the thermal conductivity gauge is best shown as curves where the sensor signal basically is drawn on the x-axis, and the actual pressure is drawn on the y-axis. You take a look at the upper graph, you will see the actual pressure here from 10 to the -4 to atmosphere. You will see the sensor signal, which is quite all right in that part, but starts to deviate very drastically for some gases in the upper pressure range. So the various curves are basically the calibration curves for different gases. You have argon here, you have nitrogen in the middle, you have helium and hydrogen here. So that means that the limitation of a Pirani gauge really are for light gases and noble gases in the higher pressure range. Ionization gauges, hot ionization gauges, or hot cathodes. They are available for UHV and even XHV pressure measurements. And that's the thing where electrons are being sent out actively using basically a heated wire, just as you know in your just as you know it from your old incandescent bulbs, Glühbirnen for the German-speaking part. The naked sensor looks like that. You have a little cage. You have some electrodes here. You have actually this is the wire that's being heated, and that sends out the actual electrons. And the actual sensing of the pressure, so counting the current pulses, is being done in that part. Okay. And of course, you can combine that kind of sensor with combine that kind of sensor with electronics. You can include displays, and that's just an example of another product of MKS. For example, our 390 micro ion ATM gauges. Physical representations or technical realizations, rather, of cold cathode gauges can look like that. If it lets me. Here we are. Sorry about that. Cold cathode transducers.
Sorry for just, we have 40 minutes now already. Thank you.
I will conclude with that slide and 3 more slides that I'm going over very, very quickly with. So cold cathodes can look like that. If you are interested, you can take a closer look at the actual sensing element on the lower left side of the gauge. Cold cathodes are as hot cathodes, being able to measure from 10 to the minus 11 all the way up to atmosphere, which is about here. We spoke about gas-dependent measurements. If you want to know which gases have what partial pressure, you can use another means of, well, if you like, measuring the pressure by determining the gases that are included in a gas mixture. So you can distinguish those using a quadrupole mass spectrometer, giving you basically a partial pressure measurement. Okay? And of course, this is a whole different topic, a whole much bigger topic, and not part of this webinar. Let me conclude my presentation with a short glimpse into the future. I told you that the very first Baratron, or the very first manometer was a mercury column manometer invented by Torricelli in the 17th century. Now 400 years have moved on, and finally, we are able to replace the mercury column barometer, which is still the basis of pressure measurement, with something entirely new, and that's called the flock or fixed length optical cavity measurement. That makes use of very subtle changes of the wavelength of a given laser within various pressure regimes. It is just 1/30th of the size of the mercury column barometer that is still being used within NIST, and it even gives you a 36 times better resolution. So the future, replacing the 400-year-old mercury column manometer, is based on the fixed length optical cavity. And for those interested, go and take a look at the link given on this slide. I hope this presentation for this rather exclusive audience has given you a little bit of insight about how pressure measurement is actually being realized. And if you have questions, feel free to contact us and MKS, and I thank you for your time.
Thanks a lot, Markus. It's a very interesting topic you're talking about, and some new insights. Thanks a lot again. Do we have some questions? Can we? I think I don't. Can I open every channel, or is it?
Everyone who wants to ask a question can just unmute their own lines.
I think they are all asleep.
Maybe one question from my side. You introduced a lot of different measurement principles. Mm-hmm. What is the typical useful measurement device for a typical CVD or edge application? Well,
in CVD, PECVD, or plasma-assisted or not plasma-assisted edge processes, you have a lot of gases and a lot of reaction products. So what you need really is a device that is able to measure the pressure independently of those species. So nothing else but a capacitance manometer comes into play when measuring or controlling the pressure in a PECVD process or in an edge process in a modern vacuum application. Furthermore, there are, of course, special baratrons that will avoid condensation of reaction reaction byproducts within the measurement cell, because that would eventually avoid a good pressure measurement or even destroy the capacitance manometer. So for that kind of application, we offer high temperature baratrons, capacitance manometer, that are being temperature controlled to all the way up to 200 degrees Celsius. First of all, being able to measure independently of the pressure with a very good accuracy over 4 orders of magnitude, and heated to 200 degrees Celsius, they are also quite immune to any kind of condensation of process products. So a baratron, possibly a high temperature baratron, would be the instrument that you would need to use in such a process.
Thanks a lot. Some additional questions? Please feel free. So typically in the measurement range where we don't have access with a direct pressure measurement with the baratrons, let's say 10 to the power of -5 and below. Mm-hmm. What do you prefer, the measurement with a hot cathode or with a cold cathode?
That entirely
10 to the power of -7.
Yeah, that entirely depends on the application. There are applications where you have low pressures, but where no active heat sources are allowed. Which means, for example, cryogenic applications. You would not want to use any heat source in a cryogenic application. So you would use cold cathodes there. On the other hand, if that is egal, if that doesn't matter, I myself would probably prefer hot cathodes, because they actively send out electrons. Because when you wait for a charged particle to occur due to cosmic radiation, as you would do in a cold cathode, you would probably have to wait for quite some time before the measurement actually starts, before the avalanche that I described earlier would actually start. So instant pressure measurement at that pressure regime can be done with hot cathodes. If you cannot have heat sources, you can use cold cathodes, but have to wait. And of course, in all cases, the materials exposed to the process need to be compatible to the process gases.
Thanks a lot. I think I don't have another question just now. Thanks a lot for your excellent talk. I think we got a very good overview about the principles of the vacuum measurement. And yeah, I think we can close now this webinar. And I want to introduce you already for our next webinar. It will be next month about pressure control. Thanks a lot.
Thank you very much. Bye-bye.
Bye.